Oh, yes. Thank you. So our lovely Edge organisers did ask me to read something a bit more galaxy related tonight, and I have I think these are vaguely related to that sort of stuff. But I'm going to read you. This is from my chapbook. I'm a self-published poet. Look at that. Hey, hey. Thanks, Officeworks, publisher extraordinaire. Anyway, so this is a bit more of a somber piece. So I hope I don't bring the tone down a bit. But before we start, I'd like to tell you about a very special person that I met. I need light. See, this is why I mainly memorize my stuff. My name's Mars like the planet chocolate, she says. Nice to meet you. Yeah, hop in. I remembered you saying you were trying to get to the ferry and it didn't click, and then I thought, hang on, Mars, you could have taken them. You're going that way. Oh, sorry, sometimes my brain's like pea soup. But I thought Mars was more like bananas and custard. The thing you needed most at times and never even knew it. Her car exuded light like a spaceship on 4 wheels, and I felt like an alien hitchhiker on a road trip through the solar system. We smiled, lofty companions journeying together to the other side of the galaxy where you can catch a ferry across to Brisbane. And what had previously been a dark, foreboding road became a trail lit by starlight and rocket fuel and roadkill. Mars, like the planet chocolate, made sure we were all belted in and secure before whooshing us up, up, up. We swerved around the tails of comets. My daughter's on a scholarship on the mainland, dived over ice particles. She wants to be a dentist or a physicist or something, slingshot around Jupiter. And she brings her homework home and it all looks like alien to writing to me. And I wish I could help you, doll, but your mum's not that smart, but she's real clever, knows what she wants. Our ship is glowing as we pass satellites. Our own reflection, our own light reflected back at us as it rotates on its axis in the slow motion of space. We barrel roll through the laneways of black holes. Mars, like the planet chocolate, flicks a switch and Neptune's rings orbit vertically around us. We fling past the sun and it's all very exciting. She says, in response to me saying her daughter sounds very clever, I don't know how she does it. She travels 3 hours a day there and back. That's 15 hours spent traveling in a week. But because she's on this scholarship, well, she's real. She wants to prove she deserves it, you know. I've come into her room at night and she's fallen asleep on her books. Outside the cabin, the alfoil sky is no longer the night sky. Out here, it's just sky. And Mars, like the planet chocolate, looks past me, sees her stars, scattered by spirits in a dreaming neither of us remembered waking from. My other daughter, though, she grins cheekily. My other daughter's like, why you got to take things so seriously, sis? We stopped at the red light of Mercury. Just chill out. We're moving again past space junk. She wants to climb trees and catch butterflies. We're doing a loop-the-loop around a UFO, which beeps a noiseless cucaracha at us. I let them find their own way, she says. She'll be barefoot with some sunburnt backpacker from Io in a few years. I can see it already. We can all see the universe and ourselves in it, and we can see tentacles waving from derelict Russian spacecraft as our ship gleams a brilliant yellow shooting across the solar system, and it's all very exciting. Mars, like the planet chocolate's skin crinkles under the weight of her smile in response to my reflection of being a horrible teenager myself as the car seems to burst into white fire. And I say, you know, I'm going to make mistakes, girls. I'm not perfect. They're both way smarter than me. And I think, fuck it, you know, it's not easy being a parent. And I'm trying the best I can. And I tell them, you didn't come with no instruction book, girls. And I'm just feeling my way through like everyone else. And they know that, so they help me out a bit. We're riding a solar flare and trimming the tops of crescent moons. It used to be so easy whistling past space debris to make them feel better, barely missing a herd of whales. Just bananas and custard, you know. They used to cry from a skinned knee and I'd give them a Band-Aid and a big plate of bananas and custard to make it all better. Now it's, where's my iPod? I hate it here. And I'm like, bananas and custard? We're a small star falling to Earth, glowing from the entry into atmosphere. She's lit up her spaceship so bright we have to shut our eyes, and it's all very exciting. At the ferry terminal from Mars to Brisbane, she winks at me and is strangely quiet now, no more than a see ya, before jumping in her rocket ship and whooshing up, up, up into space. I take the dark ferry back to Brisbane and the quiet train back home and look up into the blank sky with a bowl of bananas and custard, trying to find Mars under city lights. Thank you. Thanks for letting me be all very self-indulgent there. I think I've just lost my page. But we've got Pahia as our very first speaker. Grazie, grazie, grazie. Yes, we've got Pahia as our very first speaker. She's going to do 5 minutes in sharing all that she knows in terms of her scientific background. And please keep in mind that we do questions and stuff. So that's enough talking from me. And I'm going to hand it over to our very first speaker, Pahia.
Thank you. Hi guys, how are you this evening? I'm just going to get set up the front. So my name is Pahia. That's interference. No, my name is Pahia. I'm working as an intern with The Edge for the next month. And they thought that they'd invite me up to talk a bit about my science background and what I've done with it. So in brief, my background is I studied science at UQ, I studied neuroscience and psychology, and then I went on to study a graduate diploma of science communication down at the ANU. I went and worked at Questacon. Hands up, who's been to Questacon? Nice one, thank you. I really enjoy working at Questacon. It's a big science technology centre in Canberra, specifically for children, but adults are welcome too. And my job was to take science shows around the country, so all the way from Darwin, all the way down to Tasmania, and present them for primary school and high school students. And trying to entertain a group of 100 high school students with a science topic, you can imagine, just put your mind out there, because that's how I got my stripes. And then I decided I would go over to Indonesia and work at one of their science centres. So in Jakarta, there's a science centre called Pipa Iptek, and it's a lot less resourced than, say, Questacon. So I worked there for a year as an AYAD, an Australian Youth Ambassador for Development. And it was a very interesting experience. If you'd like to have a chat about it later, please come up and talk to me. But in brief, what I had to do was help design some new resources for the Science Centre. And they wanted dinosaurs. So we're talking about a science centre that's already under-resourced, and they want me to make dinosaurs. So we go out to little shops and we find recycled styrofoam, and we get metal and we get string, and we make latex skin for dinosaurs out of PVC glue and latex. But we have to make skin that won't melt in the humidity of Indonesia. So we have all these sort of budgetary requirements. We have guys that are really well, experienced at using not much to create a lot. And you have myself trying to grapple with language and a completely different working environment. But I'm proud to say that at the end of the day, we did create some dinosaur exhibits. And so that's where I've come back from about 2 months ago. And now I'm interning at The Edge. So that's my background in short. What I'm going to talk about tonight, though, when I was in Indonesia, I was doing some talks for students and teachers about neuroscience. So I'm going to do 5 minutes tonight about how to teach kids neuroscience. And maybe you'll learn a thing or two during the presentation as well. And it's interactive, so I want you to have fun. And if there's questions, please answer them. Otherwise, it'll be just me up here with not much to say. All right. I'll just get my presentation up 1 second, please. So the brain. Neuroscience is the science of the brain. And what do we want to know about the brain? We want to know how big it is. We want to know how heavy it is. We want to know what it's made out of. We want to know what it does, how it does, what it does. And tonight, hopefully, I'll cover about 3 of those questions. And maybe we can, make it a bit interactive. So how big is the brain? I'd like everyone to take their 2 hands and put them together with a fist just like this. Here you have a very simplistic example of how big your brain is. So take it as an approximate, but that is inside your skull approximately how big your brain is. Moving right along. Oh no, actually, let me tell you first. Men's brains are bigger than women's. So men's brains are about 10% bigger than women's. However, women's brains are a lot more dense. So there's a lot more neuronal... Yes, bad choice of words. A lot more neuronal connections in a woman's brain. And evolutionary, we can see why women would need a lot more areas such as language and social interaction, and men would need a lot more of the higher functions like decision making and problem solving. So this is how big our brain is. How heavy is our brain? So I've got some simple household props up the front. We've got some Vitabrits, we have corn flour, rice, some oranges and some salt. But what I want someone to do for 100 edge points, actually let's make it 1,000,000, 1,000,000 edge points, I'd like someone to come up and help me, close their eyes and just feel how heavy each one is, because one of these is how heavy our brain is. Who's up for the challenge? 1,000,000 edge points, people, come on. Thank you. A round of applause for our volunteer, please. What was your name?
Hi.
Kai? Nice to meet you, Kai. All right, if you would close your eyes and just walk over to the table and feel, so maybe pick them up. You might be able to tell what objects they are, but one of them is the exact weight of our brain. So maybe you'd be thinking which one you would choose.
My brain could be heavier.
Your brain could be heavier. That's a nice
Maybe
observation.
that one?
The rice. All right, so Kai has picked the, sorry.
Yes, Kai.
Kai has picked the rice, 1 kilo. So the rice is actually 1 kilo. What I'd like to tell you now, Kai, is actually the oranges, if you'd like to feel it, are the weight of our brain. So our brain weighs about 1.3 kilos or 1,350 grams. But if you'd like to pick this one up, the Vitabrits, that's our closest relative. That's the chimpanzee, the weight of the chimpanzee brain. So would you like to read out how much the chimpanzee brain weighs? I think it's on the front.
375 grams.
Thank you very much, Kai. A big round of applause for my first volunteer. So our brain is about 1.3 kilos, and our closest relative, closest species, the chimpanzee, is about 375 grams. So what's going on here? Obviously, we're a bit bigger than a chimpanzee, so we have a bigger brain. But there's something called the body-to-brain ratio. Actually, I was going to ask you a question first. Can anyone tell me who or what has the biggest brain, the heaviest brain on Earth? Who has the heaviest brain on Earth? A whale? Yes, yes. A sperm whale has a brain that weighs 7.8 kilograms. Now, who has the lightest brain on Earth? Who? An ant? Close. It was a bit of a trick question because what I wanted, the answer, was a jellyfish, because a jellyfish doesn't actually have a brain at all. So the jellyfish has no brain, but the whale, right up the other end, the sperm whale, has a 7.8 kilogram brain. Now, how does a jellyfish get around without a brain? It has a neural net. So its neurons actually, it has a little group of neurons with no brain. However, the neurons react to its environment. So things like light and tides it's able to work in its environment using the light and the tides. So that wasn't very well explained. However, the body-to-brain ratio says that bigger animals, like the sperm whale, have bigger brains. However, obviously the sperm whale might not be as intelligent as we are. So what's going on? Scientists have created a new way of looking at things where they compare the body to brain, but also with how intelligent animals are. And surprisingly, we come out on top. I'm going to show you some pictures of different animals' brains, and we're going to try and guess which brain belongs to which animal. So here we have the shark's brain, and you can see already that there's quite a few differences, obviously in size, but you can see this wrinkled prune that's around our brain that the shark doesn't have much of at all. Oh my, the paper's gone. So these brains, one belongs to a dolphin, one belongs to a chimpanzee, one belongs to a cat, one belongs to a spiny anteater. Can anyone have a guess at potentially the dolphin's brain? Which one do you think belongs to a dolphin? 4, yes, absolutely. Dolphins have one of the highest brain-to-body ratios. The chimpanzee is number 1. What about the cat?
6.
6? Very close. I actually think that one is the beaver. But the cat is number 2, and the spiny anteater number 3. So why do we need such a big brain compared to our animal friends? So our brain has evolved because of what we've been doing. Firstly, we used tools and we used our hands, so our sensory motor part of our brain had to evolve. Then we decided to live in family groups, so we had to understand social hierarchies. Then that part of our brain evolved. When we were living in family groups, we used language, so written and verbal language. That part of our brain evolved. And lastly, we were living in these groups, we had to interact with other people via language, we had to use tools, so we needed decision-making and problem-solving skills. And that was the last part of our brain to evolve. But at a cost, because our brain takes actually quite a lot of energy. And I want to do a little demonstration to show you just how much of your body's energy your brain is eating every day. So I'm going to need a brain. Anyone want? What's your name, sir? Ash. Hi, Ash. You're going to be my brain today. Now, our brain takes 2% of our body, but yet eats 25% of our body's energy needs. So hypothetically, your brain today is going to eat Mars bars, and Ash is going to be our brain, but everyone else, or as many people as I can feed with my Mars bars, are going to be the rest of the body. So we'll just see how much the brain eats from this one meal of little tiny Mars bars. So one for Ash, one for you, one for you, one for you. Oh wait, another one for Ash because he's the brain. All right, one for you, one for you, one for you. Oh wait, another one for Ash because he's the brain. One for you, one for you. Oops, sorry. One for you. Wait, another one for Ash because he's the brain. One over here, one for you. One for you. One for you, and one for Ash because he's the brain. One more over here. One more, one more. Wait, one more for Ash because he's the brain. One more. Oh, we've already, have everyone got one? Oh, you got another one. One more, and one more. 1, 2, 3. No, Ash doesn't get any more. So Ash, how many have you got? 6. And what was your name, sir? Shane. How many do you have? How do you feel that Ash got 6 and you got 1? He's a bit ticked off. So your brain takes 1/4 of all the calories that you eat in every meal, which is quite a lot of energy. So not a whole lot of animals can sustain that much energy needed to have such a big brain. Also vital for our brains is oxygen. If our brains don't have oxygen for 3 to 5 minutes, then they'll start to die. So oxygen and energy are incredibly vital to have such a big brain, which is why a lot of our other animal close species don't have such a big brain. Our organs actually, as we evolved, our organs had to become smaller, and our gut especially had to become a lot smaller so that the energy and the blood resources could go to having such a big brain. Oh, there's my notes. Enjoy those Mars bars, Ash. So we don't have the biggest brain. Actually, the sperm whale has the biggest, heaviest brain. We don't have the biggest, heaviest brain, but we do have the most complex. And what I'm going to show you now is the surface area of our brain. So that wrinkled prune bit, how much neural tissue is actually involved? That piece of paper. Beck, would you like to show the piece of paper, please? So I'd like everyone to use their imagination. This is a piece of neural tissue. It's writhing with neurons. There's 100 billion neurons writhing on this. There's electrical chemical communication going wild, axons, dendrites. So this is how big the surface area of our cerebral cortex is. It's 2,500 centimeters squared. But you might be wondering to yourself, this is not how big our head is. This is not how big our skull is. So how does this amount of neural tissue fit into our skull? Would someone be able to tell me, maybe use a piece of paper to show me how it fits into the small area of our skull? Ah, lovely. A round of applause, ladies and gentlemen. How ultimate was that? So, one of the reasons that we can fit so much neural tissue is because it's folded, and that's why it looks like a wrinkled plume. And as the species get more and more intelligent, you'll find that they use this method, the neural folds, to fit more and more surface area into a small space. Now, I said there was 100 billion neurons in our brain. Now, no one has a concept of how many that is. So I'm going to give you a hint. If I was to say 1 neuron every second, so 1 neuron, 2 neurons, 3 neurons, 4 neurons, 5 neurons, 6 neurons, you get the idea. I would be counting for 3,171 years before I reached 100 billion neurons. That's a lot of neurons. So we've discussed how much energy our brain needs, how heavy it is, how big it is, why other animals haven't evolved to the same level that we have of intelligence, and how much surface area and neurons are in our brain. So let's explore our brain a little bit further. I want you to take your hands, and here's a lovely science word, palpate your head. So first off, I want you to take your hands to the back of your head, and you'll feel there's like a semicircle of bone, of skull. And below that, it's sort of squishy. The top of you can feel your spinal cord come up, and there's a semicircle of bone. You're actually palpating your cerebrum. All right, your cerebrum works on balance, movement, and coordination. If you were to damage that part of your brain, unfortunately, your motor skills would be affected. So you wouldn't be able to ride your bike. Your eye movements, so your decision to look over there would be quite difficult. And the decision to reach out and scratch your nose, you wouldn't be able to do tasks like this. If you just go a bit above the semicircle, you're actually touching your occipital lobe. Now, I don't recommend falling off your bike at any point, but if you're going to fall off your bike, don't hit your occipital lobe, because this is where all your vision is processed. People who have damage in this area have vision defects. For example, they might have word blindness, so their eyes work perfectly well. They can see, their eyes are seeing letters, however, the part of their brain which processes what they see isn't working, so they can see letters, they just can't read. So that's called word blindness. There's a condition where you only see the right half of things. So you see perfectly fine, but if you're asked to draw a landscape, you'll only draw the right half of things. So part of your visual field, you are not actually able to process or understand. You have trouble with reading and writing, and you can't identify colours. So we've got the cerebellum at the bottom, the occipital lobe. If we go just above our ears, so if you feel just above your ears, you're actually touching your temporal lobe. Now, temporal lobe works a lot on your hearing, your auditory, because it's right near your ears, so that's lucky and convenient, isn't it? So your auditory memories and a lot of your visual memories are processed there. It processes some of your auditory, like words and reading are processed there, but also things like your identity and your sexuality is found there. So people with injuries in the temporal lobe have increased aggressiveness, they can't recognize objects, and their sexuality changes. They also talk non-stop and can't recognize faces or simple objects. Just above your temporal lobe is your parietal lobe. So right on the top, if you're wearing a headband, your parietal lobe is up here. And this is starting to get more and more advanced the closer to the front of your brain we get. So the parietal lobe processes a lot of your sensory information. So all of the information from your 5 senses, and also all of your motor cortex. So the motor cortex is there processing all the motor information to make you walk, coordinate yourself and talk. So people with there you go, you can hold that. Thank you. People with problems in the parietal lobe can't process tactile sensations. They can't feel things. They lose their ability to orientate their body in space. So the ability to balance and coordinate it is all part of the way you feel where you are in space. So spatial coordination. You can't tell the difference between left and right, and you lose your hand-eye coordination. And lastly, if you're going to fall off your bike, don't hit the back of your visual cortex, your occipital lobe, or the front, which is your frontal lobe, because all of your higher cognition happens up here. So you have your sequencing, your decision-making, your problem-solving, memory, personality, all that happens up in the frontal lobe. And people with problems up here, actually I'm going to tell you a bit about a story about Phineas Gage. He was injured in the frontal lobe, so I'll tell you a little bit more about that. Lastly, there's the brainstem. So that's right at the back, don't push too hard, but just under your cerebellum is your brainstem. And this is how you survive. So this was the first part of the brain to evolve. It regulates body temperature, heart rate, breathing, balance, movement, swallowing, and vertigo. So what I want to show you is a picture of Phineas Gage. Oops, that's... This is part of your sensory motor cortex. So some parts of your body are a lot more sensitive than others. And I really like this guy. He's a sensory homunculus because it shows you the parts of your body that are more sensitive and therefore have more brain associated to them. So obviously your lips, your hands, your feet and your genitals have a lot more of your brain associated to them because they can feel more. That's what we've just covered. And this guy is Phineas Gage. So I'm going to finish up with Phineas. Phineas was working in the road, he was making roads in America, in Vermont, in the USA. He was using a crowbar to ground up some explosives because they were going to blow up some rocks to make the road. And what happened was that when he was grinding away, the crowbar created a spark and the explosive blew up, blowing the crowbar through his head. I'd just like to show you how. Straight through behind his left eye. Now you think this would happen to anyone and they wouldn't be very well. However, Phineas Gage in a few minutes was up walking around, so he was all right. So they patched him up and sort of sat around to see what would happen. And his wound got infected, so his family made a coffin, but his wound got better, and he was all right. He managed to live out his life. However, he had quite a few personality changes, and that's what's interesting about the injury in that part of the brain. So before he was hurt, Phineas was a very conscientious worker. He was the leader of the road team who were making the roads. Afterwards, he eventually lost his job because he became fitful. He was irrelevant. He was using gross profanity and showing himself in public. This is their words, not mine. Impatient. He was ready to argue. Obstinate, if you will. He was capricious. He made plans for the future, but then in the next few minutes he would change them. He was in between two worlds, it seemed. He would change his mind often, become violent and uncontrollable. So he ended up losing his job, but he did live out his life. And some of those attributes are because of being injured in the frontal cortex. It's so vitally important for who we are as humans, our personality, that being injured up here, even though you're still alive, you lose a lot of what it is to be human. Then the part of the story that I like the best is that he walked into the Harvard medical school and said to them, "Here's my crowbar, please display this, and when I die you can have my skull." So now there's the crowbar and the skull next to each other in the Harvard Medicine Hall. So if you ever get over there, have a look out for Phineas Gage. Thanks guys, and enjoy the rest of your night.
Up next, Her name is Tamara Davies, and I'll just rudely read from this. Dr. Tamara Davies is an award-winning astrophysicist with over 45 publications, including 2 Nature papers. She is ranked in the top 1% of the most highly cited astrophysicists worldwide and has spent time helping design a space telescope for NASA. Tamara enjoys making science accessible to the public and regularly gives popular talks. She's appeared several times on ABC Radio, twice on Catalyst, and written 2 feature articles for Scientific American, including their cover story for July 2011. Tamara specializes in interpreting astrophysical observations in terms of their implications for fundamental physics. There's like a haiku in that. There's so many syllables. It's a poetry joke. Sorry. Her work is directly related to this year's Nobel Prize-winning research, and she has worked with all 3 of the Nobel Prize winners. She performed cosmological analysis for 2 of the most prominent international supernova surveys in the last 5 years, and has now returned to Australia to work with the Wiggles Dark Energy Survey, making the largest ever 3D map of the distribution of galaxies in the universe. Her aim is to understand our fundamental laws of nature, and she uses the data to test new theories of gravity and quantum physics. Her achievements were recognised by the Astronomical Society of Australia, which awarded her the Louis Webster Prize for Early Career Research 2009. In the same year, she has also received the L'Oreal Women in Science Fellowship, given to only 3 researchers across all areas of science in Australia. Recently, the Australian Institute of Physics awarded her their Women in Physics Lectureship for 2011, and she won the overall Queensland Tall Poppy Award. To top it off, as well, there's a little bit more. Tamara has competed at a representative level in 6 sports and is a qualified ski instructor, gymnastics coach, and surf lifesaver. Did you get teased heaps when you were in high school for just being like awesome at everything?
I was once described as the coolest nerd that someone knew.
Wow.
I'll take
Are you
that.
married?
Not yet. Interested?
Me. Later. Coffee. Let's go. These days, ultimate frisbee is her sport of choice. I love you. And she's just returned from the World Championships in Italy, where she captained Australia. Ladies and gentlemen, Tamara Davies.
Thank you very much. That was an exhaustive sort of introduction. You've done some thorough research there. I am surprised that anyone knows that much about me. But anyway, thank you very much for having me. It's my pleasure to come here and be the mad scientist for the evening. I hope you'll appreciate a bit of mad science. We're going to do a bit of mad astrophysics tonight because that's what I know the most about. And the first thing I was going to ask you is, what kind of mad astrophysics ideas do you guys know about? Because I've actually started to research some things that really a lot of people would consider to be fairly crazy. So here's a bit of a list of some things that I wanted you to think about, whether these are crazy propositions or whether these are being seriously considered. So things like there are atoms of space-time. Space might not be continuous. Is that serious or is that ridiculous? The idea that we have discovered thousands of planets. Is that true? And that Pluto is not one of them. We'll get to that. Is there a center to the universe? And are you at its center? Yes? Maybe? Does anti-gravity exist? Do aliens exist? Can you watch The Big Bang on your television? And do we know about, we've postulated that these things called black holes exist, but have we actually ever seen one? And does gravity bend light? These are a few questions that I thought, since we were talking about mad science, these might qualify as sufficiently mad to address tonight. Does that sound like a bit of fun? Excellent. Okay, so I like going back and reflecting on what we've learned in the last 100 years of physics. And it's quite astonishing, if you go back 100 years ago, to realize what we didn't know collectively as humankind that time. We had a theory of gravity that was Newton's theory of gravity. We didn't have the theory that we know today, which was thanks to Einstein. We also basically didn't understand much about how atoms work. We didn't have quantum physics, which is one of the big advances of the modern era in terms of particles and stuff. In terms of astrophysics, here is one interesting thing. So in 1930, we discovered Pluto, and I'm not sure if you can see on this particular backdrop because this is a little bit speckly and I'm showing you a dot. But Pluto is here. And no, you can't even see it on the other one. But that is the discovery image that found the planet Pluto. And then this is Pluto in 2006, looking remarkably pissed off because we demoted her from planet status. Does anyone know why Pluto is no longer considered a planet? There was a few yeses. Do you want to yell up an answer? Because it's a rock! Oh, okay. Is the Earth that different? It's a bit of a rock as well. Yeah, Eros! That's another excellent example. Basically, we discovered that Pluto is just one of many objects out in that orbit. So all of the other planets like the Earth and Jupiter and stuff have the orbit all to themselves. But Pluto is basically one of many objects in like an asteroid belt way out there. So, you know, people said, oh, you know, students already know that there's 9 planets. Why would you make them sort of rewrite all the textbooks and get rid of Pluto? Well, it was either that or add the 40 or so objects that we now know share Pluto's orbit, or add and keep adding as we discover more and more. So we're intrinsically lazy people as astrophysicists. We're not very good at memorizing things, and so we decided, get rid of Pluto, we'll call it a dwarf planet, and just make things easy for ourselves. So anyway, Pluto is, we don't call Pluto a planet. However, ooh, cool lights. Anyway, it's nice of them to put on a light show for us since we're doing astronomy tonight. Particularly because every time that this terrible part of me sees the lights shining into the air and thinks, damn light pollution, we can't see the stars. But anyway, planets, we know of all the planets around in our own solar system, but we've now actually managed to observe many planets around other stars. This is a picture of the launch of a space satellite called Kepler. It's a space telescope, and the purpose of Kepler is to measure or to look for planets around other stars. Before Kepler launched, we'd already known of hundreds of planets around other stars. In the first couple of years of Kepler's operation, we now know of thousands of planets around other stars. And this picture, if you can see it, is a picture of, not all of them, just a selection of the planets Kepler has found. And not only the planets, but the solar systems. Here you can see each one of these is planets orbiting a star. And you can see the distance at which they orbit, you can see how fast they orbit, and you can see that all of these ones here are actually multiple planet systems. So not only have we found planets around other stars now, but we can see other solar systems as well. And it's actually possible that there might be life or something on some of these. Most of these are pretty close to their star, so they're not naturally where you would expect to find life like us, because it's a bit too hot. Nevertheless, we expect to find a lot more, and the search for life on other planets is something that used to be science fiction, but is very much now something that people are actively doing. Not just with SETI, looking for intelligent aliens using radio telescopes, which SETI is the search for extraterrestrial intelligence. That's been going on. They made the movie Contact out of it. But now what we're going to do with some of the planets that have been discovered here is some of them just happen to pass between us and their parent sun. So imagine if you're sitting there and this is the sun, the planet passes in front. As it does that, it does sort of like a mini eclipse. And it dims the light of the star. That's actually one way where you can detect planets, by the star actually fading briefly. But the really cool thing is, if that was the Earth, then the Earth has a bit of an atmosphere. And the atmosphere of the Earth would absorb some of the light, but some of it would pass through. And you could measure the spectrum, the rainbow of light that you see from that star. You can measure the absorption from the atmosphere of the planet, and you can detect the kind of elements that are in that star, or on that planet, in that atmosphere. And if you find things like oxygen, for example, which isn't stable, oxygen burns, so if you have oxygen, it tends not to hang around for very long, O2. If you find things like that, it indicates that there's something there on the planet generating oxygen. So if you saw that from Earth, it's an indicator of life. So in the next 5 or 10 years, we're actually expecting to be able to look at planet atmospheres and look for signs of life. So it's a question that we can actually really scientifically address now. And what was once previously something that would be very much mad science is no longer the case. Now, thinking back 100 years, one of the most remarkable things that I think is the perspective-changing worldview that when we discovered there were galaxies outside of our own. So about a century ago, there was you could see a couple of fuzzy things in the sky. There was stuff like this, which is a nebula in which stars are forming. It's just a whole bunch of gas that's in our galaxy, in our Milky Way. And there's other stuff that looks a bit more like this. Now, the resolution isn't very good, but you've got here what's another spiral galaxy. But the problem was, at the time, there was no concept that there were galaxies outside of our own. And these spiral nebulae, that they were called, were not realized that it was actually something just as big as our own galaxy, our own Milky Way, and billions of light years away. It was thought that it was much closer and maybe like one of these star-forming regions. So distinguishing between this, which is a star-forming region with several hundred stars perhaps, or tens of stars being formed in it, from this, which has more stars in it than we have neurons in our brain, as I just learned. There's on the order of 300 billion stars in a typical galaxy. Now, that is a real sort of amazing thing from the perspective. It just made our universe so much more enormous than we had previously thought that it was. Now, in 1929, this guy here, his name's Hubble. He's doing two things that we never do at a telescope these days. Can you see him down there? Can you pick out what he's doing? Pardon? He's looking through the eyepiece of the telescope. Unfortunately, well, probably fortunately, digital cameras mean that we don't do that anymore. We just sit in our little lit-up computer rooms in the telescopes and watch while the data gets downloaded. You can do much more accurate things, but it loses a bit of the romance of standing out in the telescope looking through the eyepiece. He's also, you can't really tell, he's smoking a pipe. We typically don't do that these days either. Now, it was a female scientist called Henrietta Swan Leavitt who discovered that there's this particular type of star that is a standard candle. You know how bright it is. It's a variable star. And that was the key thing that allowed us to figure out distances. Because if you know how bright something is intrinsically, then just by looking at how bright it appears, you can tell how far it is away. It's known as a standard candle. So if I had a candle here and I dashed forward and held it in front of your face right here, and then I dashed back to the stage and held it up here, you could make a decent guess at how far I was away just by looking at how bright it appears, because you know how bright candles typically are. So that let us measure distances, and that was the thing that revealed that these spiral nebulae were not in our own galaxy. They were much, much, much further away. Now, the second piece of information that they had was the redshift. So you get a spectrum of light from the star or from the galaxy, and the lines get shifted if they're moving. And all of the galaxies appeared to be moving away from us, which is bizarre, because if you just had random motion, you would expect some to be moving towards, some moving away, but everything seemed to be moving away. And the discovery that Hubble made was he realized that the ones that were further distance were moving faster. That's the key thing that was the discovery that the expansion of the universe. And if you reverse the clock and watch that happen in reverse, it implies that all of the galaxies at one point would have been crashed into each other. They would have been on top of each other. And that's basically the discovery of the Big Bang theory. So that happened in 1929. Now, since then, Hubble, there he is with a more clearly smoking his pipe, we've been trying to figure out whether the expansion was going fast enough that the galaxies had the escape velocity. If they had enough velocity to escape their own gravitational attraction and expand off forever, or whether gravity would win the battle, slow the galaxies down and make the universe recollapse. So there's no smaller question than asking what the fate of the universe will be. But the thing is, that's much, much harder to measure than just measuring the fact that the universe is expanding, because you have to measure how it changes with time. And there's a picture of the Hubble Space Telescope, which was named after this guy. But it wasn't until 70 years after Hubble's discovery that we were able to actually measure the acceleration or the expansion of the universe and see which of these options was true. So here you have one where this is the example of a universe that expands forever, and the one over there is the one that shows a universe that expands and recollapses. So now we had to wait till the 1990s, which was when it was discovered that there's another type of standard candle, not a variable star this time, but a star that explodes. It's a type 1a supernova, and these things are incredibly bright. When they explode, the single star exploding can outshine all of the stars from an entire galaxy. So that's 300 billion stars are outshined by one single explosion. Now that means that as long as we can see galaxies, we can see supernovae. So we can see these things really, really far away. And in astronomy, when you look far away, you're actually looking back in time. If you're looking at something that's billions of light years away, you're looking at the universe as it was billions of years ago. Now, we looked at that, compared the velocities that you see at those times to the velocities you see at the present day, and that told us how the expansion has changed over those cosmic times. Does that make sense? Maybe? A few nods? So when it was discovered that you could use supernovae this way, two teams got together, two competing teams. On the left you have a guy called Brian Schmidt. He led the high redshift supernova team. He works at the Australian National Uni. And on the right you have a guy called Saul Perlmutter. He ran the Super Cosmology project out of Lawrence Berkeley Lab. And I've actually worked with both of these guys actually as my bosses simultaneously at some point. Here they are, they're just play fighting at a physics conference, pretending. They really were pretending. And to explain it, to give you a sort of a sense, I'm not sure if it's going to work on this screen, but I wanted to give you a visual sense of how far away these supernovae are that we can see now. So I'm going to show you a video that starts looking at a Hubble Space Telescope image and zooms out and splices that image onto other images from bigger telescopes to give you sort of a sense of how far away we're able to see with modern telescopes. So this is an artist concept, but this is actually a Hubble Space Telescope image. And as you zoom out from that, you get spliced onto other star fields from different telescopes. And you zoom out, and you zoom out, and you zoom out, and you keep zooming out until eventually you find something that you might find familiar in the sky. So I'm not sure if you could see that, but you can see the depth, the distance which we can now see. And it's thanks to being able to see this far that we were able to measure what's happening, what the fate of the universe will be, because we can measure how much the expansion is changing and figure out whether it would expand forever or recollapse. Much to their surprise, what they discovered is that none of the proposed suggestions were true. The universe is not slowing down. The universe is actually speeding up. Now, that's as bizarre as if I took something here, threw it up in the air, and watched it accelerate off into space. It means that gravity is working in the opposite direction. What was that? I missed that one. That's how strange this actual observation is. It means that either there is something out there that has an anti-gravity force, or our entire theory of gravity needs revision. So it's really a fundamental shift in our understanding of the universe. And this is a quote that I like from Frank Herbert. It says, "The beginning of knowledge is the discovery of something that we do not understand." That's what we've found now. We don't understand it. We still don't know what's causing the acceleration of the expansion of the universe, but it's now firm enough an observational result that they won the Nobel Prize for it last year. And I was really, really pleased that I got a little invitation to go to Stockholm and actually celebrate with them when they won the Nobel Prize. I didn't actually get to go to the main ceremony, but I got to go to all the after parties, which were the fun bits anyway. So to summarize the kind of stuff that is in the universe at the moment, I was going to show this. There's two main things going on. I've been talking about the acceleration of the expansion. We don't know what it is, but we give it the name dark energy. That pushes everything apart. You may have also heard of dark matter. That does the opposite thing. It pulls stuff together. It's been known for about 40 years because galaxies spin too fast to hold themselves together, and if there wasn't some extra mass there that we couldn't see, then they would fly apart. That was the initial discovery, but since then we've confirmed that discovery of dark matter in many different ways, including gravitational lensing of light. So yes, light does bend around galaxies, and in fact, this picture on the left is a picture where you have a cluster of galaxies in the middle, and there's a few blue things here. Can you see that? There's a blue thing there and a blue thing there. Those are actually the same galaxy. But what you're seeing is that the light from that galaxy, the galaxy is basically almost directly behind this cluster that's in the middle. So this is in the foreground, and the blue galaxy is in the background. The light, the gravity of the cluster in the foreground acts like a lens. So the light that was travelling outwards and would have missed us gets pulled in by the cluster, and then approaches us and comes at us actually from multiple different directions. So we actually see the same galaxy from different directions. And that's a confirmation of a couple of fantastic things. Firstly, general relativity. Einstein's theory of gravity predicts this and how this works. But also the existence of dark matter, because again, the amount of bending that we see can't be explained by the amount of luminous matter that we see. There has to be a whole bunch of dark matter there as well. And dark matter can't be something that is made of atoms. It doesn't interact electromagnetically. It doesn't interact with stuff like you and I. It has to be made out of something else. And there's hope that they might actually create that in something like the Large Hadron Collider, which is now operating in CERN. You may have heard it discovered the Higgs boson recently. And but we don't know. But that's one of the major mysteries of physics at the moment. We're trying to explain dark matter, and we're trying to explain dark energy. Now, I've got a bunch more slides about things like some black holes and stuff, but does anyone have any questions at this point before I go on a little?
I can bring microphone around if you have questions. Hands up, class.
Yeah. I'll let you think of questions. I'll show you my next slide, and then I'll ask again. So if you think of questions in the meantime, and if you have any, get ready. Okay. This here is an image of the black hole at the center of the Milky Way. Now, who's heard of a black hole? Now, black holes are black. They don't really emit light. They might glow, they might evaporate a little bit, but we're not going to talk too much about that. In essence, black holes are basically just things that are really massive, really dense, so dense that from inside the black hole, light can't escape. Now, here there's a time-lapse image. So if I start the movie here, what you see, this is actually a picture that's taken, not a picture, but it's a time-lapse of the center of our galaxy and the motion of stars in our center. This is taken with an infrared camera so we can see through the dust that's obscuring the center of our galaxy. And you can see, remarkably, that there are stars that orbit something that isn't there. There's a blank spot here And that was where that cross was in the original image. And that blank spot is right smack bang in the center of our galaxy. It's not glowing, and yet all of these stars appear to be orbiting it. Now, if you look at the time scale on the top left there, that's over about a decade of observations watching stars move. And we've watched this guy do a complete orbit. So when you do the calculations, if you see an orbit, you can measure the mass of the thing that it's orbiting about by looking at how fast it moves and measuring its distance. When you do the calculation, the mass of the thing that it's orbiting has to be billions of times the mass of our sun. And the only thing that can be is a black hole. So this is some of the best evidence that we have for that there's a black hole at the center of our galaxy. And in fact, we now are very confident that there are black holes at the center of every galaxy. Some of them are the very young galaxies especially, the black holes at the center are sucking in so much gas that they appear to glow very, very brightly. And the reason that they glow is not because the black hole is glowing, but actually because the gas falling into it gets compressed and gets really hot. And so you see these black holes by the gas that is falling into them before it actually crosses in over the event horizon. Okay, any questions at this point? We can save all the questions for the end then because I've got a few more slides that I'd like to show you before we're completely done. Now this is a picture of the Big Bang. It's a very interesting picture. It's actually a picture. If you look out in every direction on the sky and you project it onto like the normal sort of thing, like you would do projecting the round Earth onto a flat map. This is an all-sky picture taken in microwaves of what the temperature of the universe is like. What you're actually seeing is an almost entirely perfectly uniform glow of radiation from all directions, which is actually the afterglow left over from when the early hot dense universe. So at one point, if you go back for the Big Bang, the whole universe was hot and dense as a star. And then the universe expanded, it got more dilute, and the leftover afterglow from that really hot dense time is still everywhere. It's travelling around from all directions. The stuff that was near us is now over near distant galaxies. But that radiation is still travelling around. It hasn't hit anything. So this is light that basically has come from the Big Bang. It's about 100,000 years after the Big Bang, which is a eye blink in astronomical terms. Now, you know how I mentioned that at the beginning I asked you whether it was madness that you could watch the Big Bang on your television? It's not. If you have an old analog television, then some of the static that you see on that television is actually because this radiation is emitting in the range that your TV can pick up. And so some of the static on your television was genuinely you were watching radiation coming from the Big Bang, which I thought is sort of cool. Anyway. If you look in more detail at this radiation, if you subtract the average part, you can actually see a dipole. You see a hot in front and cold behind. What that is because we're actually moving with respect to this radiation. So you see the hot spot in the direction that we're moving towards and a cold spot behind us. Now if you subtract that, you see something that looks like this, which has some smaller fluctuations. You see that our galaxy glows in microwave radiation, which is this. And so you can see our galaxy as a stripe through the middle. But if you subtract the galaxy again, then you end up with something that looks like this. This is taken with the Wilkinson Microwave Anisotropy Probe, which is a telescope that's up in space at the moment. Or it's finished doing its observations now, and there's a new one called Planck that's trying to do a better job. But here, if you imagine yourself being at the center of this sphere and look out, this is what the fluctuations in the microwave background look like. These are tiny fluctuations on the order of 10 to the minus 5. So it's almost perfectly smooth, and then there are these tiny little fluctuations on the perfectly smooth. And the hot and cold spots that you see in this map are the things that have eventually made the clusters and voids, the galaxies and the spaces between them in the present day universe. Because what happened was these were the seeds of structure formation. And we can now, in our computer simulations, start an expanding universe off, and you start to see starting from that very almost perfectly smooth initial condition with tiny fluctuations, you can see gravity pull structures in and make galaxies grow. Now, this is a computer simulation made by one of my colleagues down at Swinburne University. His name's Greg Poole, and it's a cluster of galaxies forming in the universe. Something like our own Milky Way would want to be one of these little fluffy blobs around the edge, and this is the biggest cluster that was forming in the simulation. Now, watching it on this background doesn't really do it justice, so if you'd like to check it out in full resolution, come and check out my computer when we're done. So the story that we have of the universe is it starts from something that looks like the cosmic microwave background with small fluctuations, and it slowly forms into the galaxies that we see today. Now, it was mentioned in the introduction that one of the things the reason I moved back to Australia was to join a survey which is actually called the Wiggles survey, because we're looking for those wiggles in the galaxy distribution. And we used the Anglo-Australian telescope to make the biggest ever three-dimensional map of the distribution of galaxies in the universe. This is me hanging out on the dome of the Anglo-Australian telescope. This is some of our data. It looks like spectra. It's pretty boring, except for the fact that the light that we're seeing, again, is coming from a really long way away. So there was a lot of excitement when you're at the telescope and you see something that's from a really great distance. This is a typical one. This light was emitted on the order of 6.5 billion years ago. So I'm not going to go through what the little lines and stuff mean here, but I had a really exciting moment at the telescope when I saw this messy-looking sort of scribble. Because I saw this, and this was not what I expected to see. And I was like, what is that? I went to my colleague, and I said, Darren, what's this stuff? And he's like, that's a quasar. And because I'd been looking at the completely wrong distance for this. This is actually light that was emitted 12 billion years ago. And you get a bit of a thrill when you see that at a telescope, because this formed 4.5 billion years ago. So the Earth is about 4.5 billion years old. So the light that we're seeing was emitted before the Earth even formed. So it was emitted, it's been travelling through empty space, not hitting anything. Meanwhile, a dust cloud starts to coalesce, a star turns on in the centre, some planets form around the outside, you get the oceans forming, some little things crawl out of the oceans and eventually learn to build telescopes, and the first thing in that whole time that the light has hit is the mirror of our telescope. So it's very exciting when you see that kind of thing. So you're not going to be able to see these photos at all, but this is a cool picture. This is the picture of the Earth taken from the moon by the astronauts on the moon. And I just thought I would conclude with a bit of reflection of our place in space, because when you realise how empty space is, how far light can travel without hitting anything, and the first thing it hits in 12 billion years is our telescope, it makes you realise how precious it is what we have here, and really how valuable our own Earth is. Now, this is also a picture of the Earth. Some of you might think that it looks a little bit like Saturn, but that's because you're not looking close enough. That's the Earth there. There's actually a tiny little dot. This is taken by the Cassini spacecraft. It's on the other side of Saturn and it's looking back towards Earth. And it actually managed to take a snap of Earth as a tiny dot through Saturn's rings. This is also a picture of the Earth, which, again, you can't see it all. However, it's there. It's a tiny dot, and there's a couple of stripes in that image which basically show the sort of the sunbeams. It's just refraction from the lens of the camera that's taking it. But this was taken by one of the Voyager spaceships, and it's the most distant photo ever taken of the Earth itself. And you can see, all you see the Earth is this tiny little dot sitting in the vastness of empty space. And it's one of the reasons I find astronomy quite inspiring because it does give you this perspective. It gives you a chance to study the universe as a whole. It gives you a chance to understand things like anti-gravity might exist. And it gives you a chance to study how the fundamental physics works. And it also gives you a really good perspective of where your place is in the universe. So to come back to where we started, which of these are seriously being considered? Well, all of them are. Everything that I mentioned is really basically a serious proposition in astrophysics at the moment, which is why I think it's legitimate to call some of, it's a mad science. It's quite fun to play with. So thanks very much, everybody. I will leave it there.
Thank you, Tamara. Any quick questions? Hello there.
Hello, Tamara. That was a wonderful presentation. I've got a question for you. What do you think of time travel, and could you explain it?
Absolutely. Okay, wait for 2 seconds. Okay, we just travelled in time. Time travel sort of happens all the time, in the sense that we are travelling through time, or at least we perceive ourselves to be. Time travel it's interesting because it's a legitimate possibility in general relativity. In fact, the major difference between Newton's theory of gravity and Einstein's theory of gravity is that time and space are no longer immutable in Einstein's theory. So if you move quickly, time travels at different speeds for you compared to someone else. So we already know it's very legitimate that if I want to stay young and watch everybody else age, or if I want to find out what happens on the Earth 1,000 years from now, I just leave on a spaceship, travel as fast as I can, come back, and if I'm able to travel close to the speed of light, I can make it back, and thousands of years may have lapsed here on Earth for only, say, a year of my time. We know that's possible. We've actually done the experiment with atomic clocks in jumbo jets. You need atomic clocks because the amount of speed that they achieve is so small that you see only a very, very small amount of time dilation there. But it actually has been measured and confirmed the prediction of relativity. So that's one way to do it. Also, time travels differently close to the Earth to far away from the Earth. Now, most people, when they talk about time travel, though, is not just travelling into the future. You really want to travel into the past. And relativity actually does make that possible in theory as well. There may be reasons why it doesn't happen, but it's something that's an active area of research, because if you can warp space enough, you can make something like a wormhole, where you have one piece of space over here connected to another piece of space over there by some sort of tunnel that sort of cheats and goes, and you can go backwards in time that way by using the malleability of space and time. Who knows whether this is possible? Most of the theories of time travel that use wormholes say that you can't actually travel back in time till before the first wormhole was created. So maybe it's something that we will figure out how to do, and the only reason that we haven't seen time travelers now is because we haven't created our first wormhole yet. So we'll have to say the jury's out on that, and we'll find out what happens.
Wow. My time travel information comes from watching the second Alien film. But that's great. We've actually run out of time, so we're going to have to cut it short. We'll do one quick question.
I'll try and make my answer shorter this time.
No worries.
Based on the velocities of galaxies and things, are we able to pinpoint the origin of the Big Bang, like the location of it, or approximately?
Aha! Are you willing to give me 5 more minutes to explain that? Yes. Where is the center of the universe is basically the question that you're asking, right? Because luckily I did have something prepared on exactly that question. And so the center of the universe actually just happens to be here. We did an exhaustive search, and I can now confidently say that you are the center of the universe. And so I'm actually not... I'm being partly facetious, but it's not entirely facetious. Now, so let me explain. What was discovered is that when Hubble discovered the expansion, galaxies at greater distances are moving faster. Now, that means that, so if looking from our perspective, galaxies nearby are moving away a little bit slowly. Galaxies further away are moving faster. And so it looks like we are at the center of the universe, right? But the story is that that actually is true for every observer. Now, okay, so I need a couple of volunteers to help me demonstrate this. So since you asked the question, would you like to come up and be one of the volunteers? And I might need 2 more. Yes? Anyone else? You looked eager. No, 1 more volunteer. Yes, thank you. Okay. So what was your name? Lee over here. Christine. And Maggie. So these are my galaxies. Lee, Christine and Maggie, and I'm going to be here in the middle as well. So stand in a line here, and I'm going to see if we can say, so we're evenly spaced galaxies at the moment, but we're going to start close together, and I'm going to make the universe expand around me, because, that's what we do. So you guys are nearby to me, so you guys just take 1 step away, while Maggie, takes 2. So if you all step away, the universe has just expanded. But now we're going to do something different. Now we're going to make Maggie the center of the universe. So if we all come together again, now this time you're going to take 1 step, I'm going to take 2 steps, you're going to take 3 steps because he's moving the fastest. Ready? 1, 2. So it doesn't matter which point you choose is the point of this not particularly good demonstration, but it doesn't matter which point you choose. Any point you choose, it looks to them as though everything is moving away from them. Okay, thank you very much, volunteers. I have another visualization of this as well. So imagine these dots are galaxies in the universe, and then imagine that this is a slightly expanded version of that universe. Now I've gone and I've taken these and put them on top of each other, and you can see where the expansion is emanating from there, right? Now unfortunately I have to get rid of the presentation mode of this to be able to do this, so just 1 second. Oops, I'll do it this way. And so here, if I now pick up the top one here, maybe I'll make this galaxy here the center of the universe. So we move that there. Can you see how everything now looks like it's moving from there? Or what about this galaxy in the corner here? If I pick that up and move it, now everything looks like it's coming from that corner. So you can pick any galaxy here and move it till it matches, and everything will look like it's emanating from that. So the reason I can say that you're the center of the universe is there really is no center of the universe, and there's no location where the Big Bang started and started expanding. It's just that every single position, everything is moving away from everything else, and the fact is that space is expanding between the galaxies rather than the expansion happening into some sort of pre-existing space. So I hope that goes some way to explaining that popular question. Thanks for asking it.
Awesome.
And thanks again for having me.
Thank you, Tamara.